Thank you, Martin. I'm Michael Buser, and I'm going to provide a brief overview of the agricultural data management landscape from an administrative view. Brief overview of our initial USDA level efforts to develop a national geospatial enterprise architecture to support a digital agricultural research community, and then give a rapid glimpse into a few of our more targeted grassroots efforts to develop standardized, integrated, and automated digital solutions for agricultural researchers. If after today's session you want to know more about our current efforts, please send me an email at pdi@usda.gov. As a national program leader within USDA Agricultural Research Service, or ARS, I attend meetings and calls weekly with researchers, industry partners, and agricultural stakeholders. These calls are with internal ARS folks, university partners, other federal agencies, state agencies, and others. Common topics of conversation on many of these calls include artificial intelligence, machine learning, and deep learning. After amazing discussions about the incredible advancements our agricultural research community is making, someone always asks the tough questions. Why aren't our farmers, ranchers, and processors putting these new advancements into practice? We are spending tens of billions of dollars annually on agricultural research. Why aren't we advancing more rapidly? Before I address these tough questions, I'm going to reflect a little on my past. In preparing for this presentation, I began to think about the many challenges that we face today in agricultural research. Then I began to think, these topics sound familiar. I went back to my files from about 25 years ago when I was a student and later a research engineer at Oklahoma State University, working with some incredible faculty members, Drs. Brown, Stone, Soley, Whitney, and Ron. These faculty members provided me and others the incredible opportunity to work on several AI and ML projects. Projects such as SPICE-2, which was a project for mapping contaminant transport in rock formations, or the development of precision farming tools like VRT and what later became known as GreenSeeker. Yes, 25 years ago, we spent a lot of time talking about the need for more computational horsepower. But when you get beyond that, many of the issues that we had a quarter of a century ago are the same issues we have today. All 7 of the data management issues or challenges listed on the screen come from researchers today. These were also big issues 25 years ago. A couple that stick out to me as a national project manager include data silos and loss of legacy data. These two stick out to me the most because I know we're spending tens of billions of dollars annually on agricultural research, collecting an incredible amount of research data, and we're not even coming close to gleaning the full value from these investments. USDA agencies, individual research units within ARS, individual universities, and even individual researchers are working in siloed environments. We need a paradigm shift where we eliminate these silos and we share experimental data not only related to our successful advancements, but from our experimental failures. Within the ARS, researchers are retiring at an alarming rate, and it is common to lose 30 plus years of knowledge and data when folks leave the agency. This is also a common occurrence in academia and industry. Within USDA, we have incredible vector, tabular, business, imagery, IoT, and analytics assets and data management systems. However, these assets and systems are not linked and suffer from standardization, integration, and automation issues. USDA has some incredible siloed systems. For example, the agricultural census, plant hardiness zone, forest inventory, conservation management, and fire management. Can you imagine the impact and value of these various data assets and systems if linked in a standardized and optimized manner? Think about the duplication of effort that could be reduced and the economies of scales that could be captured. Think about the interactions that we might now see because we no longer have the blind spots between program or topic area silos. Just imagine the possibility of entering a federated portal to access any agricultural or environmental data, model, or decision support tool that has been vetted or re-engineered to exist within a national systems of systems that has a federal level authority to operate and is following federal cybersecurity guidelines. We can. USDA already has some incredible platforms. For example, BigMap was launched in 2017 as a prototype to conduct scalable analysis of large-scale imagery data assets. This is an elegant solution that is using harmonic regression procedures to process something like 38 times the Earth's surface for a 5-year time period on 4 raster analytics servers to process something like 21.7 trillion pixels of information in less than 33 hours. We're not looking for a single solution. We're looking to develop a system of systems based on the best-in-class approach. Within USDA, we do have systems that pull data from other USDA or federal agency systems to produce audience-specific informational materials, visual data dashboards, and decision support tools. Tools such as the Broadband and Precision Ag Dashboard pull data from the NASS crop data layers, Ag Census, and FCC Form 477 into an interactive tool customized for targeted audiences. In 2020, the state of the USDA geospatial capability included pockets of world-class geospatial excellence, pockets of emerging geospatial architectures, pockets of expertise, and pockets of cloud services with minimal connections between these pockets. A few months ago, we officially started a USDA-level effort to develop a concept, roadmap, and a pilot for a national geospatial enterprise architecture. The primary goal is to develop a state-of-the-art digital system of systems for agricultural data, decision support tools, and models. We also want a system of systems where all systems are interconnected through data pipelines. The pipeline construction is to be optimized in terms of economics, functionality, and end user experience. For example, if I do a query in AgCross for soil carbon, I want to make sure that I find the soil carbon data that is in FSA and Forest Service. USDA leaders are seeking best-in-class solutions that can be implemented on a national stage. We want to learn from groups that are excelling in this digital world and apply this knowledge in developing an interconnected, high-performance systems that can drive future agricultural research forward more rapidly. Our agricultural leaders have presented us with the Agricultural Grand Challenge to minimize our environmental impact while producing enough food, fiber, and fuel for an estimated 10 billion people. And we need the solutions by 2050. Many agricultural leaders believe we need to develop national and global data management systems that are standardized and integrated using more automated data collection technologies to meet this challenge. In 2018, when I started my role as National Program Leader for ARS, I had a number of industry leaders encourage me to have our scientists be more involved in the development and maintenance of data standards. Figure out how to develop and implement national and global data management systems for agriculture. When I first received this input, I pushed back and informed our stakeholders that this is not what ARS is designed to do. And the typical response I got back was that these are issues that need to be solved. And if USDA cannot solve these issues, then who can? So based on this stakeholder encouragement, in June of 2019, USDA ARS officially kicked off Partnerships for Data Innovations, or PDI. In June of 2021, we officially kicked off our project focused on developing a USDA National Geospatial Enterprise Architecture. with USDA Office of the Chief Information Officers, GIO, Global Science and Technology, Esri, North Carolina State University, and others. This USDA National Geospatial System of Systems architecture is focused on integrating all types of data. Upper USDA leadership is focused on developing an architecture that extracts more value out of the data and tools that are being developed for agriculture today. We are looking to minimize duplication and maximize automation. We are looking to make systems interoperable, and we're not looking for a one solution fits all. We are looking to develop a dynamic design that can evolve relatively easy as technology advances and scale as demand increases. We want an architecture that can help us drive future innovation. Our development team is working this problem from two different directions at the same time. We have a team that is focused on engaging all USDA agencies to determine the basics about the data they are collecting, hosting, or adding value to, and the decision support tools or models that they serve out. We want to know the current baseline of these resources. Then we want to know how these agencies would like their data systems to work if there were no barriers. Do they use data from other agencies or groups? Could they use data from other groups instead of developing their own data resources? If they could lean on another group for data resources, what would they be looking for? Coming from the other direction, we have systems and solution engineers working on developing baseline system architecture, using what we currently know about the current needs and best-in-class systems. Yes, we do fully expect to have to adjust as these results from our informational gathering start to bear fruit. However, we are betting that these adjustments will be minor in comparison to starting from scratch, hence getting us to a prototype pilot more rapidly. So how do you architect such a system to support multiple programs, reduce duplication, promote automation, and drive cost efficiencies? Let's start with the basics. First, we recognize and try to leverage the Federal Geospatial Data Committee, or FGDC, work to architect solutions across the federal government. Specifically, the left-hand side of this image covers the principles of the shared services model that's based on FGDC's approach to enterprise geospatial management. The first point is that geospatial is at the core of many U.S. federal agencies. And as such, you need to build your systems around the fact that all data is inherently spatial. Some might argue that not all this data is spatial, but we would counter argue that you maybe haven't collected all the appropriate metadata, so the spatial nature of your data is not represented. The second point is that you must follow a series of architectural principles, or namely, you need to focus on geospatial standards, develop good user experiences that serve multiple communities, and strive for automation and promote the reuse of assets. The right-hand side is typically how you implement these principles or concepts. Computer scientists call this the N-tier or three-tier architecture, which is designed to promote reuse of assets between tiers and segregation of functions across data, applications, and user interfaces. I will show several slides that ground this in reality, but the idea is to acquire data, structure it according to the nature of that data, and contextualize it in map stacks or layers and hydrate different user interface models that best fit the user's desired experience. The first example of our N-tier architecture is from PDI's support of crop data products as they relate to applications like precision agriculture. First, data come from several sources, including Landsat, producer or user surveys around crop plantings, climate data, and even user input from cellular or mobile devices. Several geographic information products are created, such as crop data layers, agricultural intensity around the big five commodities, and areas that comply with the FCC broadband requirements. These geographic information products can feed into several interfaces that serve multiple communities. For example, if you want to see if agricultural area is served by broadband, you can combine two of the layers from the middle tier to develop the Precision Ag Broadband Dashboard. Or if you just want to find out where crops have been over the past few years, you can use a custom app such as Cropland Cross. Each of the products or decision support tools can use multiple layers or information products, which can come from multiple data sources and be processed using complex workflows to generate information products. The application and decision support tools can also feed information from user inputs and engagement metrics back into the system to be used for future activities, creating a circular data pipeline. The same paradigm can be applied to other parts of USDA, including the Farm Production and Conservation Business Center, or FPAC, who have systems that directly work with producers. FPAC uses the same model to process high-resolution NAPE data that works with a variety of systems, like Esri's Living Atlas or Google. This is an example of USDA systems that are assets to USDA and a variety of commercial entities. As a final example, I mentioned the Big Map system earlier. Big Map from the Forest Service is an excellent example of cloud-based processing at scale. They combine 80 years of field plot data with 35 years of Landsat data, process it through several image processing routines like harmonic regression to produce an array of informational products listed here, ranging from forest type identification to quantification of forest carbon. These products feed into Sustainability Modeler and other decision support tools. While the three previous in-tier architecture examples are great, we would consider them agency-level systems that are purpose-built for standardization, integration, and automation. They serve as a combined system of records for various USDA functions. As mentioned before, the next step is to integrate these various in-tier systems together into a federated architecture glued together by a central hub, making up shared services or web services architecture. In this way, we aggregate the system agencies to present a unified view of USDA mission areas. We call this a system of systems, or more commonly, a hub and spokes architecture. And this is what USDA is starting to build out. This hub and spoke approach centralizes exposure of content delivered by mission area programs and seeks to leverage a governed distributed landscape of geospatial and related technologies. The department-level GeoHub system will not only connect agency data pipelines together to promote cost efficiencies and interoperability, but will also serve as a hub of applications and analytical models. Think about a user looking for soil carbon data and being able to find all USDA soil carbon data through a single interface, or running crop insurance models that can automatically link to the most current data across all USDA agencies. In this context, the GeoHub becomes more than just an aggregation of data. It expands the capabilities of our current models and decision support tools. It develops a solid foundation for our future AI and ML systems that will be needed to help us achieve our 2050 Grand Challenge. I have talked about our plans and current efforts to build up a federated geospatial architecture, or USDA hub and spoke. I started with a nth tier architecture. I then walked through the concept of connecting those systems into a system of systems for all of USDA. But now I want you to think bigger with me. Think about scaling not only government, but private industry, academia, our farmers, ranchers, and processors, and even the American citizens. That system of systems now becomes a system of systems of systems. How might this type of geospatial enterprise architecture help farmers, ranchers, processors, researchers, regulatory agencies, consumers, and even Congress achieve the climate smart agriculture goals that Secretary Vilsack discussed last week in Colorado? Now that I have you thinking big, I'm going to draw your attention to the red dot down at the bottom. One national data management system within one USDA agency. The USDA Agricultural Research Services Partnerships for Data Innovations, or PDI. PDI is working on developing several data-related solutions, and I want to spend the next little bit giving you a little insight into what a single USDA spoke is working on today. PDI is actively working with over 400 researchers across the U.S. on a wide range of research topics. We are working with several universities, other federal agencies, state agencies, and private industry. Although this is a national project being led by ARS at a national level, it is very much a grassroots initiative. PDI is focused on developing customized digital solutions that meet our researchers' needs. Our goals are to develop digital solutions to help decrease the time and effort researchers spend on data management so they can spend more time on their research. Unfortunately, I don't have enough time to dive deep into the schematic, so I'll discuss it at a high level. Items in the green boxes represent PDI's Living Data Management Scientific Workbench. Within this workbench, PDI is actively working to expand the AgCross data standardization and integration platform, develop external data pipelines to sources such as Ag Data Commons, NOAA, USGS, and others, develop customized data collection apps for observational data, evaluate connectivity solutions to improve the transmission of data from the field to the cloud, develop automated linkages between continuous monitoring sensors and our GeoEvents servers, and develop semi-automated QA/QC workflows. Develop optimized regional laboratories for common sample analysis. And now shifting to the red boxes labeled Decision Support Informatics, or DSI platform. We just last month started working on DSI. The DSI platform is our stakeholder resource platform. The goals are to get our agricultural research into the hands of our stakeholders in the most economical, secure, functional, and user-friendly manner possible. Over the past 6 months, we've been evaluating an off-the-shelf product designed to help researchers develop, share, maintain, and track their research methodologies and SOPs. The researchers that were brought in to evaluate the off-the-shelf product provided a recommendation that we should move forward within implementing this cloud-based technology. I am pleased to announce that we have just finished the initial installation, and we are rapidly moving towards a broad ARS rollout in the coming months. I'm not here to promote one off-the-shelf product over another. I am simply reporting that we have identified needs from the researchers in the field, and we are actively looking for solid solutions that we can implement across ARS. We are looking forward to evaluating how our researchers utilize this new resource. PDI's data management platform, AgCross, is designed to give credit where credit is due, while standardizing data with the AgCross Data Dictionary. This provides us the ability to integrate data across researchers, locations, and networks, all while giving credit to the respective network, location, and researcher. The standardization and integration of data within AgCross provides users the ability to query data across locations and networks. For example, if we were to query nitrous oxide data within AgCross, in seconds we could see a graph like this one, showing mean nitrous oxide values from 30 different studies that are included in AgCross and have their data permissions set to publicly available. ARS has an incredible amount of historical data, some of which dates back to the early 1900s. PDI is actively working with a number of research groups to standardize and integrate historical or legacy data sets. We are also working on a couple of efforts to integrate databases that are end of life. Although creating value from historical data is extremely rewarding, it is one of the most difficult PDI efforts that we are undertaking today. PDI is actively working with a number of research groups to develop customized data collection tools for capturing observational data. Most of these tools are device agnostic. Currently, we're working on apps for tick disease, citrus screening, dam engineering, cotton, and others. This is an image of our farm management app for the farm crew at the Beltsville Agricultural Research Center. Members of the farm crew can select the plots that they're going to work and then enter data specifically related to tillage, planting, spraying, irrigation, harvesting, and other activities. Once the crew member enters the data is pushed up to the cloud, and all local researchers that have permissions can immediately view the data. We currently have versions of this tool developed for 6 of our research locations. These apps are currently undergoing testing. While the locations are testing the customized interfaces, the PDI technology team members are rapidly standardizing and integrating the data fields from the 6 customized apps to the AgCross data dictionary. In the next couple of months, we're hoping to initiate conversations with a large number of ARS work sites to customize this base app for their specific location needs. We have a large effort focused on pushing continuous monitoring data from data loggers to our cloud-based GeoEvent servers. The goals are to make real-time data readily available to our research community and local stakeholders. We have a separate effort focused on developing semi-automated QA/QC software that will help our researchers complete the QA/QC processes more rapidly. Once the data has been checked and approved, the data will be moved from the GeoEvent server into the AgCross environment. We have many efforts focused on data visualization. This includes interactive dashboards with drill down capabilities and online maps. These interactive tools are proving to be highly valuable to our stakeholders, researchers, and upper leadership. Although ARS has a large number of continuous monitoring systems out across the country, our researchers are always looking for additional data. So PDI is working with our private partners to develop data pipelines to other data repositories like NOAA and USGS. These dynamic data pipelines are being designed to evolve based on economics, functionality, and user experience. We are also working on expanding the development of our search and discovery tool. This tool is designed to allow our users to select an area of interest and retrieve a shopping cart of the data available for that area of interest. The user can then select specific data from the shopping cart and download it. We're just scratching the surface on possibilities with this new tool. PDI is working with other federal agencies to develop customized interfaces. For example, PDI is working with the National Agricultural Statistics Service on the development of Cropland Cross, a new interface for the NASS crop data layers. PDI is working with several private partners. Sometimes PDI's role is bringing 2 companies together to integrate their technologies. A recent example of this is TrueTest and Esri working together to help PDI develop a set of customized solutions for collecting and using data for researchers working cattle. We have Microsoft TV white space technology installed at our Beltsville location. In 2020, we conducted spectrum evaluations at 5 additional research locations across the country. The spectrum data is key for improving our connectivity at our research locations. Our goals are to improve the connectivity at our research locations to take full advantage of data automation technologies. We are focused on improving connectivity across all of our acres using the most economical and secure technologies available. PDI is standing up a pilot regional byproduct, plant, soil, and water laboratory. The goal of this pilot is to optimize all laboratory components to improve quality, minimize sample and data touches, increase capacity, maximize equipment utilization, and decrease cost. Our researchers have estimated that we can increase capacity at our pilot lab from about 40 to 50,000 samples per year to about 450,000 samples per year, and decreasing the average sample cost from about $15 per sample down to about $3. PDI has been working with U.S. private companies to develop a U.S. manufactured UAS. This UAS was designed to work specifically with the Esri SiteScan software. We received our first 2 Astro units a couple of weeks ago, and we're looking forward to evaluating these new solutions. We have a brand new effort working with ARS and university researchers and Esri. Our goals are to build off of the Ag Gateway ADAPT platform to help our researchers standardize and integrate the data coming off of agricultural field equipment through an automated system. Again, our primary goals are to decrease the time our researchers are spending on data management and improve data quality. Developing a strong agricultural research community that shares data, tools, and knowledge will be one of the fundamental keys to meet the 2050 Agricultural Grand Challenge to minimize environmental impacts while being able to feed, clothe, and fuel our future population. Thank you for your time today, and I'm looking forward to your questions.